So for extra credit, if somebody emails me Thursday night to remind me to put the Go Fish cards in my backpack so that I remember to bring them in so we can finish the mono invariance and show why you do get the number 1 card to eventually be on the top. All right, so there was a suggestion today to do integration, to do some problems from calculus. And so I thought that was a really good idea. There are some sheets here. One of them is just a generic Virginia Tech math exam. I'll try to get a little closer. That's not even going to work. All right, so you can pick that one up later. And I've also just compiled a bunch of problems over the years that involve integration. So because one person was confused, it says, 17th Annual Virginia Tech Regional Mathematics Contest from 9 a.m. to 11:30 a.m., October 28, 1995. Fill out individual registration form. Problem number 1, evaluate the integral. And then it moves on to the 18th Annual. That does not mean it should take you 2.5 hours to evaluate the integral. I'm just showing the first problem. Okay? So evaluating integrals using techniques from calculus, this is extremely common. So here is a nice question. So 2 of my colleagues like to have debates. One of the topics they debate is E versus pi, as to which one is better. So better is a loaded word. So instead of using better, I will use bigger. So which one is bigger? Okay. Can somebody give me a way to figure out which one is bigger? I'm sorry, compute them. How would you compute them? Mathematica, calculator, okay. That's one way. All right, that's cheating. Okay? You are marooned on a desert planet. There's an EM dampening field. It's from Star Trek. No technology works at all. You can only use, fingers, stuff like that. All right? How can you prove in an entirely elementary fashion e to the pi or pi to the e, which one is larger? If you want a hint as to how to approach this and how to use calculus to start this, let me know. Okay, so that's the first thing I want you to be thinking about. The second one, which we will discuss in class on Wednesday, no, I'm sorry, this is Wednesday, on Friday, is I think my favorite problem from Calc 1. So you have the number 100, or in general, you have the number s. And in the first variant of the problem, what we want to do is we want to split the number into pieces so that the product is as large as possible. All right, so we did get swiveling restored, but it doesn't seem to want to swivel too much. So let's try to help it a little bit. So split into integers so that the product is maximized. And the sum is 100, or more generally, s. Okay. So if I'm doing something like this, I have too many smartasses in this class to give you this problem as stated. Right? So what must I assume about the split in order to stop you guys from giving me something stupid? So the numbers, they have to be integers, they have to add to s. I want the product to be as large as possible. Non-negative, right? Because if I allow you to do negative numbers, you can have 2 negative numbers. Their product will be positive, and you can play these balancing games. So, I'm sorry? Negative 200, negative 200, positive 300. The sum, I'm sorry, positive 500. The sum is going to be 100. Right? So you could make you could drive the product to infinity. Is something not stated?
What are we summing?
You want it, well, if you come to class, and you are splitting a number into integer pieces such that their sum is 100, and you want the product of the pieces to be as large as possible. So we want the pieces to be non-negative. We can actually do a little bit better than non-negative. What else can we do? Positive. And with a little bit of work, you can actually do a little bit better than positive.
Probably not 1.
Probably not 1, because does 1 help you at all for the product? No, so each is greater than or equal to 2. So that's problem 1. Problem 2 is redo, but now only require real values. So I want you to then figure out what is the largest product you can get if you split 100 up into pieces such that the sum is 100, the pieces are positive, but now you're allowed to use real values. Okay? Is everybody clear on these problems? There's some extremely important mathematics and computer science behind this. This is not a make-work problem. And the solution can be done entirely elementarily. It involves a lot of techniques from this class, and it's a great way to review essentially all of Calc 1. So almost all of Calc 1 comes into play in looking at this. Okay. So now the suggestion from class, I've had 2 suggestions so far. One is to do more like logic theory, riddles, problems like that, and one is to do some integrals. So I just put up a couple of integrals. And so let me start with, here's one. Integral from 0 to pi over 2 of sine cubed of x over sine cubed of x plus cosine cubed of x dx. So a lot of times in math competitions, they do give you integrals like this to do. What do you know about any integral given to you on a math competition? It's easy, you can do it, there is a way around it, there is a trick. What do you know about integrals given to you in life? For the most part, not necessarily easy. For the most part, you can't do it. But there are good things to do, there are things you can try. When you see something like this, what's your first thought whenever you see an integral? Integration by parts.
Trigonometric things.
Trigonometric things. U sub. Anything else? Derivatives. Is there an antiderivative? Okay, so let's assume we tried everything and everything has failed. There is another word you should be thinking of. So when you take a class with me, if you don't put down the word area, when I ask you to say the fundamental theme of calculus, wrath happens. And I get very upset. I'm watching The Incredible Hulk right now, the TV series with my kids. Something very close to that happens to me when people state the fundamental theme of calculus without mentioning the word area. And so I'm trying to keep myself calm right now. But not area here. There's a word we should be thinking of when we see something like this. Not calculator. That's one of the 7 words you can't say in a math class. What should we be thinking of when we see something like this? No. Symmetry. Whenever you get integrals, you should always be thinking about symmetries. When you look at this, is anything symmetric? Is anything nice? Sometimes it's the missing or the hidden part. If I gave you this integral is not what you would want to integrate. If you could change the integrand, how would you change the integrand? No. Nope.
Add a cosine cubed on top?
Sure, right? Wouldn't you love to have cosine cubed up in the top? Can you just add a cosine cubed? You would have to then subtract cosine cubed, right? So I would love to add the integral from 0 to pi halves of cosine cubed x over sine cubed x plus cosine cubed x dx. And if I do this, what do I I get pi over 2. I'm integrating the function 1 from 0 to pi halves. So I can add this, but then I have to then figure out what the integral of cosine cubed is. Is there really any difference between trying to figure out the integral of cosine cubed over sine cubed plus cosine cubed? No. Can you think of any relation between these two? So how does symmetry help? Yes?
What is it? Sine is the same thing as cosine but displaced by...
Good. So which way do you want to do the displacement? Do you want to do the displacement in the cosine or the displacement in the sine?
Doesn't really matter.
Doesn't really matter. So sine of x is cosine of, let's see, cosine starts off at 1. So maybe we want to do cosine x minus pi halves. So this would be cosine plus sine. Yeah, so that would work. So sine cubed is the same as cosine cubed of x minus pi halves. Well, that's essentially just running things backwards. So there's still work to be done here, but this is beginning to give us an idea of what's going on. There's a lot in common between sine and cosine. Now we're integrating from 0 to pi halves. So when you have symmetry, you often want to be symmetric about a certain point. What might be the interesting point here? Pi over 4. So maybe something interesting is happening around pi over 4 in terms of trying to relate what's going on. At the end of the day, what do you think is going to be true about these two integrals?
Equal.
They should be equal. And that with some kind of change of variables, we should be able to make this integral equal that integral. Right? So we have a couple of things to be looking at. We could be writing x as maybe pi over fourths minus t, and t goes from maybe minus pi fourths to plus pi fourths. We could write sine of x as cosine of x minus pi halves. When we now have that up here, how do we now shift things? So there's lots of different games we can play to try to make these two expressions the same. I want to pass from this integral to this integral. And so does this equal this point-wise? Are these integrands the same?
Can't you just like replace, say that they're the same, like cosine cubed in the middle itself, but minus pi over 2 is 0? And then,
I'm sorry?
oh, that like, sine cubed, the sine integral equals the cosine integral from minus pi over 2 to 0 using that identity.
All right, so you want to shift the region of integration.
Yeah.
But then we also have to shift things down here.
Oh, like, that. Do that.
But now when we shift things, if we shift things, we should still have a sum of cubes. So we're reduced to showing these two things are the same. So one thing that you might want to do is maybe when x is close to pi halves up here, that might be close to the value here, maybe where x is close to 0. You know, maybe there's some kind of exchange we can do between them. We want to show that these two integrals are the same. So it all comes down to showing that they're the same. Right? So we want to show these are the same. What's the easiest way to do this? So if I start off with this, if I write sine of x as cosine of x minus pi halves, you know, I could use this identity and say that this is the same as the integral from 0 to pi halves. Sine becomes cosine of x minus pi halves cubed over sine cubed x plus cosine cubed x dx. Okay. Now, how do I want to handle this? This is almost what we want. Yes?
Don't we also need to change the sign cubed on the bottom? Like we changed sine x into cosine x minus pi over 2 at the top of the fraction.
So this was to use the identity.
Yeah.
And so I just used the identity on the sign. Do I want to use the... So right now, this is true by the identity. So now the question is,
Why can't we use the identity down?
we could use the identity again on the bottom, but we want at the end of the day to end up with just a cosine cubed over. And so here, x runs from 0 to pi halves. So I'm going to start off at negative pi halves and go all the way up to 0. I could actually switch this to be pi halves minus x if I wanted. And so there's lots of different ways. I'm not sure right now which way is going to work best. This is 0 to pi halves cosine of pi halves minus x cubed over sine cubed x plus cosine cubed x. And so I'm beginning to fear that this is going to bring me down into too long of an algebra. And so now I would want to do maybe some kind of translation. Let t equal x plus equal maybe pi halves minus x. And so if I do something like this, when x runs from 0 to pi halves, t is going to run from pi halves down to 0. This will now give me a cosine cubed, and I'll have sine cubes and cosine cubes. Maybe I can somehow now reduce things using the trig identities below. And if I try that, I will get over here the integral from 0 to pi halves. Oh, no, I'm sorry. Now I'm going to go from pi halves to 0. I've flipped the order, right? Because I'm letting t be pi halves minus x. So now I'll get cosine cubed t up above, which is good. Now sine cubed of x, x is the same as pi halves minus t. So I'll get sine of pi halves minus t cubed plus cosine cubed of pi halves minus t. And now dt is negative dx. So that negative sign will then switch the order of integration again. So now I have cosine cubed. I have sine cubed pi halves minus t. Well, what's the relation of sine cubed of pi halves minus t to cosine?
Cosine.
So this becomes sine cosine. So it looks like there's going to be a negative sign there. But it's fine, because sine of pi, okay, so if we multiply this out, sine of pi halves minus t is sine of pi halves cosine of t minus cosine of pi halves sine of t. Well, the only term that survives is the first term, which is going to give me, I think, a minus cosine. And so it looks like I'm off by a minus sign. Because over here, I'm going to get cosine cosine plus sine sine. And so we've made a small algebra mistake somewhere in the flipping. Does anybody see where the algebra mistake was done? So the question is, was this correct? Is the sine of x the cosine of x minus pi halves? Was that right, or did we make a mistake there? This becomes cosine x cosine pi halves, which is 0, plus sine of x sine pi halves. So I believe that this is correct going from here to here. Now we want to change variables. We'll let t be cosine of x. Cosine is an even function. I can write that as pi halves minus x. So if I let t be pi halves minus x, we then get x, no, we get x is pi halves minus t. And so now this stuff over here would become sine of pi halves minus t plus cosine cubed of pi halves minus t. And so now when I look at this, this is going to be sine cosine. Oh, wait a minute. Oh, no, that's fine. This is going to become, this is just going to be cosine of t. It's sine cosine minus cosine sine. We're fine. We're fine. Okay. The minus sign reverses things, and we integrate from 0 to pi halves. The top is cosine cubed of t. And then the sine cubed of pi halves minus t, that's going to just be the sine cubed of t. And what we're using here is we're using the sine of pi halves minus t is sine of pi halves cosine of minus t plus the cosine of pi halves the sine of minus t. And if you want, the minus sign comes out over there, and you get cosine cosine minus sine sine. And now, what's the cosine of minus t? Cosine of t, sine of pi halves is just 1. And so you get just cosine of t. So down here, this term becomes cosine cubed of t. Now we have the cosine cubed of pi halves minus t. This is cosine pi halves cosine t plus sine of pi halves sine of t. That's going to just be sine cubed of t. And so at the end of the day, we have the integral of sine cubed over sine cubed plus cosine cubed is the integral of cosine cubed over cosine cubed plus sine cubed. Does not want to swivel. So with stuff like this, it sometimes takes a while for the algebra to work out. The main idea in problems like this is symmetry. Look for what's missing. They frequently give you an integral that's really nice, but they only give you half of it. And so you have to find what's the other corresponding piece. Sometimes you might need to expand about certain points. In this problem, we didn't need to expand about the point pi over 4. But I wouldn't have been surprised if maybe we want to match things by expanding about the point pi over 4. That's extremely common for stuff like this. Then it's knowing some of your identities. So whenever you have these trig problems, you've got to know your trig identities. Okay? Maybe later today, I will teach you how to prove every trig identity in 1 minute or less. There's a great way to rederive all trig identities. But I want to just make sure first we're clear on a problem like this. Is this a function that we can find an antiderivative to? No, not even close. So in problems like this, what you have to remember is they're not asking you to find an antiderivative. If you could find an antiderivative, would it be easy to integrate? Yes. But you can still integrate it without knowing the antiderivative. That's the trick. Is for problems like this, whenever you see bounds of integration, the bounds of integration means there's a nice answer over the entire region. Over smaller regions, there may not be a nice answer. So I'll give you another example. This is a standard example where over the whole thing it's difficult, but over a small region it's not so bad. So consider the integral from 0 to pi halves of sine squared of t dt. There's a very nice answer for what this equals. So there's lots of ways to do this. What's missing? What would you love to have? You'd love to have cosine. There's several ways to do it. One of the simplest ways is to say, well, look, this is 1/4 the integral from 0 to 2 pi of sine squared t dt. And if I do it like this, I don't have to really worry now too much about how do I change sines to cosines, what's the phase shift. I'm going over a whole cycle. So for a lot of problems like this, you sometimes want to go over a whole cycle. For the problem we did a moment ago over here, why can't we go over a whole cycle? So I'm curious as to, it is still tracking, but why can't we go over a whole cycle? Why can't we extend the integration in the previous one to be from 0 to 2 pi? Okay, so
No, I think that then you have to worry about like it being negative.
and so the denominator can actually be 0, right? So when I get to like 3 pi over 4, I think the denominator will be 0. And so we can't extend this to all of 0 to pi and then take a shortcut trick like that. But in other problems we can. And so over here, I can extend this to 2 pi and then just take 1/4 of it. Now, this is clearly the same as 1/4 of the integral from 0 to 2 pi of sine squared t dt plus 1/4 the integral from 0 to 2 pi of cosine squared t dt, all divided by 2. And the reason is, since I'm going over a whole period, sine and cosine take on the same values. And so now this is just 1/8 the integral from 0 to 2 pi sine squared plus cosine squared, 1. All right, we've come this far, we might as well finish the problem. So we integrate 1, we get 2 pi, we divide by 8, we get pi over 4. If I had asked you to integrate sine squared from 0 to pi thirds, that would be a lot harder. It's doable. There are formulas for the antiderivative of sine squared, but they're not as easy to work with. The complete periods or quarter periods, these are things you want to think about. What do I need? How many copies do I have to get the whole thing? These are huge ideas in problems like this. Okay. The other thing is, do you believe my algebra? Do you believe pi over 4? Whenever you get an answer, you should always ask, is it reasonable? Does it pass the smell test? I would be very concerned about what it would look like if I tried to smell this white powdery thing on the camera, so I will not do that. But does this pass the smell test? Does this seem reasonable? What do you think? Tell me why pi over 4 could or could not be a good answer. Yes?
So on the interval 0 to pi over 2, sine squared will be 0 at 0 and 1 at pi over 2. And so if you think just a plain rectangle that covered that area would have an area of pi over 2, and we kind of cross through the middle of it.
Sure. Sounds good. Do you like the pi? Yeah, I mean, we've got a pi in the bounds of integration. If I got an e over here, would you be suspicious? I would be suspicious of an e. A pi is reasonable. Now going to what was said, it's 0 at 0. It's 1 at pi over 2. What do you want to hazard as an average value of sine squared? A half, right? Take the average between your minimum bound and your upper bound. So if we take the average of the two extremes, we're integrating the function that's 1/2 from 0 to pi halves. What would we get? Pi fourths. It's a reasonable answer. It's about the right size. It's smaller than pi halves. It's kind of using the average of the two extreme values. Ballpark, this is reasonable. Okay? All right, so this is a huge idea of the missing part of the integral. And when you put it together, the integration becomes easier. But again, we're not doing the closed form antiderivative. We're doing the complete integral. How many of you are damn comfortable with your trig identities? If I asked you to come to the board and prove the angle addition formula, you could do it. How many of you are comfortable with stating them? All right, I'm going to show you then how to do all of this in, it shouldn't take us more than 5 minutes. So it's also a nice way to digress into some good mathematics. How many of you have seen Euler's, or the Euler-Cotes formula, e to the I theta is cosine theta plus I sine theta? Okay. It is possible to go through a Williams math major without ever seeing complex numbers, but not if you take a class with me. All right. All classes through me, even Calc 3, at some point we do go through the complex plane. So I am the square root of -1. E to the I theta is cosine theta plus I sine theta. You can get this with the Taylor series expansions. e to the x is 1 plus x squared over 2 factorial, yada, yada, yada. Cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus yada, yada, yada. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus yada, yada, yada. If you just formally plug in I theta for x and put into the series expansion, then if you put all the reals together, you get cosine. If you put all the imaginaries together, you get sine. If you notice, I squared is -1, I cubed is minus I to the 4th is 1. You're going to have these things that are cyclic of period 4. And every 2 times you're going to change by a minus sign. That's why when I put in x as I theta, all the even terms are going to be real and they'll be alternating in sign. All the odd terms will be purely imaginary and they'll also be alternating in terms of a minus sign. Okay, any questions about this stuff over here? We also need e to the I theta, e to the I phi is e to the I theta plus phi. This actually requires some work to prove. This is non-trivial. The reason it's non-trivial is because we've defined the exponential as an infinite power series. And technically what this means is take the infinite power series with theta, take the infinite power series with phi, multiply them together, it's the infinite power series with this. If this were not the case, we would be guilty of highly misleading notation. When we say things like, let's call this e to the x, it is highly suggestive that e to the x times e to the y is e to the x plus y. But you have to prove that. Okay? And until you prove it, you can't use it. So what we would have to do is e to the x, e to the y is the sum, n goes from 0 to infinity, x to the n over n factorial, the sum, m goes from 0 to infinity, y to the m over m factorial. Have we done this in class? Okay, so we'll just do this really, really fast. This is the same as the sum. L goes from 0 to infinity. The sum, I'm running out of letters, we'll do k goes from 0 to L. X to the k, y to the L minus k divided by k factorial L minus k factorial. I have to be a little bit careful to show that everything converges. If I put absolute values in, we'll see I'm fine. I'm not going to worry about that. This is the little questions. If you want to see the detail of this, one of my other lectures somewhere this semester has this done carefully. Might be 389. What am I doing? I'm looking at the x's and y's and I'm grouping them whenever the sum of their exponents equals a given value. So if I look at the possible values of n plus m could be 0, it could be 1, it could be 2, it could be 3, it could be 4, it could be L. Where have you seen something like this before? We have seen something like this semester. N choose K is going on, but there's a type of mathematics. It begins with a C. Catalan combinatorics convolutions. When we're looking at products of two generating functions, we got things like that. And so what I'm doing is I'm grouping all the x's and y's together such that the sum of their exponents is equal to L. Well, if you look at the denominator, this is highly suggestive. Right? I've got a k factorial, L minus k factorial. What do you wish you had up top? Which factorial? You wish you had an L factorial. Can you just put an L factorial in the top? Sure. But if you're going to do that and feel the wrath, almost as bad as not saying area. What do I have to do if I put an L factorial in the top? Yeah, divide by, right? So there's two things you can do in mathematics. You can multiply by 1 and you can add 0. We multiply by L factorial over L factorial. And when we multiply by L factorial over L factorial, this is now just L choose k. And I can bring this L factorial outside of the k sum, and we get L goes from 0 to infinity, 1 over L factorial the sum, k goes from 0 to L choose k, x to the k, y to the L minus k. Oh, what is this over here? It's the binomial theorem. And so this then just becomes the sum, L goes from 0 to infinity, of x plus y to the L over L factorial, which is our definition of e to the x plus y. So this proves why this is good notation. If this were false, this would be some of the worst notation in mathematics. Does mathematics always have good notation? What is my least favorite example of notation? No.
It's just a line. I really can't hold myself.
What's 1 over cosine? And what's 1 over sine? I've always been bothered by that. Shouldn't you put the cosines together? Shouldn't cosine go with cosecant? And shouldn't sine go with secant? Wouldn't that be more sensical?
You wouldn't be able to say shot your cat.
So, all right. Now that we know this, I can prove now every trig identity for you. Okay? Everybody ready? Everybody comfortable with all these facts? What's the most important trig identity? Pythagoras. Okay, so the start of it all is Pythagoras. All right, so let's go back and we'll prove Pythagoras. So cosine squared x plus sine squared x equals 1. Okay. E to the ix times e to the minus ix is e to the what? 0. We add the exponents. And e to the 0 is 1. Well, e to the ix, this is cosine x plus I sine x. E to the minus ix is cosine x plus I sine of negative x. Well, the sine of negative x is just negative sine of x. Another way of looking at what's going on is when I take complex conjugates, I replace I with minus I. So if W, well, do Z, I guess. If Z is A plus IB, the complex conjugate is A minus IB. And here, AB are real numbers. If I multiply things out, cosine times cosine is cosine squared, plus I sine cosine, minus I sine cosine, they cancel. Minus I squared sine squared, well, minus I squared is minus negative 1, which is 1. So when we multiply it out, we get cosine squared x plus sine squared x equals 1. There's Pythagoras. Okay? Next is let's do the angle addition formulas. I'm going to remove these in the interest of space. So let's do, all right, so let's do e to the I theta, e to the I, well, we'll do x and y. E to the I x, e to the I y is e to the I x plus y. This is going to be cosine x plus I sine x. This is going to be cosine y plus I sine y. And this is cosine of x plus y plus I sine of x plus y. And now all we have to do is expand things out. So if we look at the real part here, we get cosine cosine minus, from the I squared, sine sine. So the real part here is cosine x cosine y minus sine x sine y. And the imaginary part is going to be sine x cosine y plus cosine x sine of y. The only way two complex numbers can be equal is the real parts must be equal, the imaginary parts must be equal. So this part over here, this must be the cosine of x plus y. And similarly, this must be the sine of x plus y. So I'll leave this to you to figure out and play and get more identities. You can get all the trig identities you need from these facts. If you do not remember these facts, you have to resort to direct proofs. And so the direct proofs can be interesting. So for the direct proofs, let's see. I will just quickly draw the picture. It's been a while since I've done this. X, Y. Geometry is all about drawing auxiliary lines. Yes. And so if you label things appropriately, you can use this to get the angle addition formulas for the sine of x plus y and the cosine of x plus y. And for this picture to work, I have to assume that x, y, and x plus y are all between 0 and 90. If they're not, this picture is false. And you can see how much more painful this is than doing it the other way. Okay, so this was a long digression, but when you're trying to do any of these contest problems involving integration, if this trig functions, you are going to need to know your trig identities. So you should really make sure you hone up on your trig identities. You should know your half-angle formulas. You should know your double-angle formulas. You should know cosine x plus y, sine of x plus y. It's probably not a horrible idea to know the tangents as well. All right, so we only have 5 minutes left, so I'll just state one or two more problems and then just start the conversation as to how we might look at them. So this problem is, I think, a Putnam one, although interestingly the printing is not great. All right, so, all right, yeah, wow, all right. All right, so let's look at the last one on the first page. This is Putnam 1987 B1. I will not ask if any of you were alive back then. This is before the Berlin Wall came down. Classic problem. It's integrating from 2 to 4 of the square root of the natural log of 9 minus x divided by the square root of the natural log of 9 minus x plus the square root of the natural log of x plus 3. And this is 1987 B1. All right, so this was a Putnam problem. When you look at this problem, what are your thoughts? No. Or that can only be true on a relative scale. You know, relative to the other problems you do in life, yes. Relative to the other problems on the exam, no. You want to spend most of your time on B1 and A1. Every now and then they make a mistake in the Putnam Committee and they actually put a easier problem later down by mistake. They try to make the problems increase in difficulty. Every now and then they get it a little bit wrong. What's your first thought when you look at something like this? We've got lots of numbers. Which numbers matter? Why do they give you these particular numbers? Which ones are squares? 4 and 9 are squares, but 2 and 3 are not, although 2 is the square root of 4 and 3 is the square root of 9. Yes?
You notice something interesting going on where you have 9 minus 2 is 7.
Good.
9 minus 4 is 5, but the same thing kind of going on with x plus.
Yeah. So if we look at 9 minus x, when x equals 2, it's equal to 7. When x equals 4, it equals 5. So this goes from 2 to 5. So did I give a, no, sorry, from 7 to 5. 7 to 5, right? And if we look at x plus 3, when x is 2, this is 5. When x is 4, it goes to 7. So it almost looks like these functions are running in opposite directions. It looks very similar to the sines and the cosines. And in fact, what you could probably do is that problem that you were given with these cubes, there's probably something general going on here. That there's a general type of problems. We have certain types of bounds. You have functions that are symmetric maybe with respect to the midpoint of that bounds, and you have this way of replacing. When you look at this problem, what do you think is missing?
wish you had the square root of the natural log of x plus 3 on the numerator?
Words you probably never thought you would say in your life. But yes, we miss the fact that we don't have the square root of the natural log of x plus 3, right? If we had that, life would be so much simpler. So when you're looking at this problem, you've got this thing that's hidden. And so maybe somehow, if I replace this with the square root of log of x plus 3, maybe I'd get the same value. And if I put that in, what do they add up together to be? So if I just put the square root of the ln of x plus 3 in the numerator and I integrate, what will I get? I'll get 1 for the integrand, 2 for the integral, 3 for the show, okay? Something like that. So if I put that in the numerator, I know what the answer is. So what would you guess the value of this integral is? I would guess 1, because the whole integral is 2. If I put that in over there, this should be half of that. Without doing any calculations, I would guess that the integral is equal to 1. So if you can't even prove anything, you can try to BS things, and you can say, noticing the symmetry and the integral is the same, 1 gets twice the integral is equal to 2, and therefore the integral equals 1. And you can try this, and it may or may not work. The higher up you go in mathematics, the more likely you are to get away with something like this. A lot of times, if you're taking oral exams for your math, you're going to be very careful. I'm pretty sure they can't take back my degrees. If you act confident, the professors will not press points. And say, oh yeah, this follows immediately from such and such and such. Okay, yeah. And then they'll move on to something else. And you're just like, please follow from such and such. Please follow from such and such. When you write things up in the pundum, they would probably want you to put in some additional details. But you might be able to get even a point for just noticing that the integral is probably 1. It depends on how generous they are. I would still spend the time and write it up carefully. The odds that you are able to productively use your time on all of the problems is so small. Spend the extra 5 or 10 minutes to write things out clearly and in full detail. Now then the question becomes, how do you want to write things? When you're doing these problems, you might want to change it so you integrate from maybe -1 to 1. And if we do something like that, we now have the integral of the square root of the natural log of, how would we write this? I think maybe 6 plus t.
Maybe like 9, 3 plus 6 minus x.
So how do we want to do this? Integrating from, do you want to keep the integral from 2 to 4? And do natural log of 6 plus 3 minus x. Is that how you want to do it? And then down below we would have the natural log of 6 plus 3 minus x plus the integral. And now we have x plus 3, so we would add 3, and we would have 6 minus x plus 3. But now we need 3 minus x maybe. Does that look right? So now this will give us, 3 plus x. So that might be a good way to approach a problem like this, is to see that I can write it as now everything is, these are the 6 plus this, these are the 6 minus. And since this goes from 2 to 4, this number is now running from 1 to -1. Right? So maybe I can replace it now with, I'm integrating from 1 to -1. And I can replace that with a t, and a t. Normally people do not like to integrate from 1 to -1, so you would switch the orders here and make this a -t. And so this just might be a useful way to start approaching the problem. All right, this is a good place to stop, so pick up, if you haven't done so already, some of these problems.